All right, so today's talk is titled Disordered Reward, Perspectives of Substance Use and Abuse. My name is Joseph Mickey. I'm a first-year psychiatry resident at the University of Oklahoma in Tulsa. All right, so some of today's objectives include introducing the research domain criteria, or RDoC, to look at the normal brain functions seen through the RDoC perspective. We'll look at approach motivation. We'll also consider disorders that may involve dysfunctional reward, and we'll look at a historical overview of drug use and abuse. We'll also look at a biological perspective of drug use and abuse, as well as looking at that from a psychological perspective and a social perspective, and finally conclude by looking at some of the interventions that can be made for substance use. Let's start off with a warm-up quiz question. The area of the brain most associated with willingness to work on difficult cognitive tasks is? And go ahead and just record your answers. And a second question is, in neuroscience, the P3 is? Again, go ahead and record your responses, and we'll take a look at these again a little later. All right, let's take a look at the National Institute of Mental Health research domain criteria. This is a framework for normal functions of the brain and is considered by some as a counterpart to the Diagnostic and Statistical Manual, or DSM, although it is not used clinically. While the DSM may focus on categorical entities, the RDoC implicitly emphasizes traits that are dimensional, or that exist along a continua. The primary functions are organized into 5 broad domains. These refer to social processing, arousal and regulatory systems, cognition, positive valence systems, and negative valence systems. Each domain is then subdivided into various constructs and subconstructs. For instance, negative valence systems comprise systems for processing fear, anxiety, loss, sustained threat, and frustration. Now, each domain and construct are further studied using 8 specific what are called units of analysis. These are genes, molecules, cells, circuits, physiological response, behavioral studies, self-reports, and paradigms. Given that our focus today is substance use disorders, let's look at the RDoC system perhaps most intimately associated with substance use disorders, which is called approach motivation. The construct approach motivation is but one of the constructs within the broader domain called positive valence systems, and approach motivation itself is composed of 4 subconstructs, and we'll take a closer look at each. Briefly, they are reward valuation, effort valuation, expectancy, and preference-based decision-making. Reward valuation refers to the processes by which we come to estimate or determine the value we place on a given outcome or reward. This may be reflected by Cookie Monster, who, as we all know, places a supreme value on cookies. Chocolate cake won't do it, money won't cut it, alcohol is out of the question. The thing that this lovable blue monster ranks above all else is cookies. Now, as we'll see, dopamine is involved in this process, and it is by far the most important molecule in the motivational system. However, interestingly, serotonin is also understood to play a role as well. I want to draw your attention to the outlined boxes. These are key features of reward valuation that we will see again when we look at the disordered motivation. These include the orbitofrontal cortex, the corticolimbic circuit with significant influence from the prefrontal cortex, and the ventral tegmental area. The orbitofrontal cortex is involved in making quick associations between stimuli and rewards. It has been called the motivation center, and has been likened to a steering wheel that helps steer our behavior towards our value-oriented actions. The prefrontal cortex has a role in ensuring our actions are aligned with goals, and this has been likened to a brake because it serves to inhibit some behaviors. The ventral tegmental area, or VTA, located just next to the substantia nigra, is the source of the dopamine neurons that are essential to the reward circuit. Now, just because we have a cookie or a carrot or a lure dangling out in front of our face doesn't mean we necessarily exert any effort to obtain it. While a greyhound may circle the track endlessly in pursuit of a lure, the sloth has decided to take a much different approach to effort valuation. Its entire existence is predicated on exerting as little energy and effort as possible while still meeting its metabolic requirements. Effort valuation is also called willingness to work. Let's take a look at one of the areas that is uniquely involved in effort valuation, and that is the anterior cingulate cortex. This area plays a major role in difficult learning tasks and encodes reward outcomes. This area also appears to be the origin of an important EEG signal known as error-related negativity, or ERN. This signal occurs when someone becomes aware that they have made a cognitive error. The strength of the ERN signal is an indicator of how well someone can learn from errors. Another key area involved is the nucleus accumbens, which is a part of the basal ganglia. The nucleus accumbens is a primary recipient of the dopaminergic output of the VTA. The next component of approach motivation is called expectancy, or reward prediction error. You can imagine this as the sudden increase in appetite and desire for sweets when you walk across the cookie stand in a mall and smell the wonderful aromas they have been pumping into the air. This is also intimately connected to the craving that may seem to blindside a drug addict who simply gets an intense urge to use when they walk past an old building where they used to get high. Monterey Jack illustrates this well, as he will be one of the best detectives and workers unless he is sidetracked by the aroma of cheese, which sets off a quest to find and consume this cheese, even at the cost of abandoning his detective duties. Dopamine is essential in this process, and often a P3 signal on EEG is correlated with dopamine production and can serve as a marker of reward prediction, or in other words, of expectancy. Neural circuits that are involved in this process include the amygdala, which play a critical role in emotional learning, memory, and preference-based decision-making, as well as the orbitofrontal cortex, the anterior cingulate cortex, and the VTA. This process of reward prediction error is very fundamental, so let's examine it in a little more detail. So on this slide, we will examine actual dopamine signal activity in response to rewards and reward cues. Let's look at the graphs here. The little dots represent dopamine release, and the bars at the top are summations of total dopamine released at any moment of time. As some historical background, in the early 1990s, Schultz and his colleagues experimented with monkeys. They presented a visual stimulus, and then the monkeys could press a left or a right lever. The left lever pressing always resulted in a juicy reward. Initially, before learning, dopamine neurons exhibited higher activity only when the juice was received. This is precisely what is represented on the first graph. Initially, when there is a reward given, but we don't know if any of our actions are producing that reward, we experience a dopamine surge only when the reward is received. Eventually, in the experiment, the monkeys learned that the left lever always produced the reward. Once this occurred, the dopamine surge happened when the visual stimulus was presented. In other words, when the conditioned stimulus occurred. This also corresponded with the monkeys initiating anticipatory licking. So when we examine this second graph, we notice just that. The dopamine spike has shifted to the conditioned stimulus, which in the case of the monkeys was the visual light. But it could just as well be the aroma of a Cinnabon in the mall making you suddenly have a desire to consume a sweet pastry item. Finally, in the experiment, if the juicy reward was not received, then the dopamine activity actually dropped below baseline level at the time the reward was expected, demonstrating that these neurons were sensitive not only to reward, but also to timing. This is shown on the final graph, where the conditioned stimulus occurs, be it the light or the aroma, or perhaps for an addict, a glance at a piece of drug paraphernalia. And the dopamine surge occurs. But if the reward is not received in a timely fashion, we see this drop-off in dopamine activity that we can relate to that sense of disappointment or of not getting the Cinnabon or craving for that hit of cocaine. Thus, expectancy, which is also called reward prediction error, is mediated by dopamine and is a motivated response based on a predictable reward attainment. And what we note from the heading is that this is a critical part of learning, where learning appears to be proportional to reward prediction error, such as occurred in the top and the bottom graphs. Just to finish off, the final component of the RDoC construct of approach motivation is called preference-based decision-making. Of note, the amygdala appears to play a significant role in this. Let's turn now to a basic model of the brain that reviews some of the important areas involved in this approach motivation and some of the specific functions carried out by those areas. The prefrontal cortex plays a role in the valuation of rewards and exerts an inhibitory role to ensure our actions are aligned with goal-oriented behavior. The anterior cingulate cortex plays a major role in difficult learning tasks and encodes reward outcomes. Error-related negativity, ERN, is an EEG signal that occurs when someone makes a cognitive error, and it is localized to this area. The strength of the ERN is an indicator of how well someone can learn from errors. The ventral tegmental area is the source of dopaminergic neurons. It primarily outputs dopamine to the nucleus accumbens. The P3 signal is an EEG signal that reflects dopamine production, and thus expectancy. The amygdala plays a critical role in emotional learning, memory, and preference-based decision-making. The orbitofrontal cortex plays an important role in stimulus reward and stimulus outcome learning, which is required for recognizing conditioned stimuli. It also signals the expected rewards and punishments of an action. Finally, the nucleus accumbens receives the dopaminergic signal from the VTA. It is a part of the basal ganglia. Having taken a look at essential motivation and reward centers in the brain, let's now turn and look at some disorders that may involve dysfunctional motivation and/or reward. There are a number of neurological and psychiatric disorders that may involve dysfunctional reward and motivational brain circuitry. ALS and Parkinson's, for instance, have been reported to at times result in excessive boredom or apathy, a pronounced disinterest in most things, perhaps tied to an aberrant motivational system. Anhedonia, the absence of ability to feel pleasure, is a classic feature of severe depression, likely related to reward processing. ADHD can be considered a defect in the inhibitory pathways that emanate from the prefrontal cortex to the reward system. And the excessive goal-oriented behavior of mania can be thought of as resulting from excessive motivation and reward pathway firing. Of course, substance use likely has disordered motivation and especially wanting, and we will take a look at this in greater detail. Motivation and reward processing have been measured in a variety of ways as they pertain to these various diseases. For instance, in most people, the anticipation of a reward is correlated with pupillary dilation. One research group found that the degree of apathy in patients with Parkinson's was correlated with reduction in pupillary dilation when exposed to reward cues. Another measure of apathy in Parkinson patients includes a 24-item dimensional apathy scale. fMRI has also been used to correlate depression with decreased anticipation of rewards, as well as reduced sensitivity to received rewards. Finally, fMRI has also proven valuable in demonstrating a link between impulsivity, not only in patients with substance use disorders, but also in the siblings of patients with substance use disorders, that corresponds to a disruption in the connection between the prefrontal cortex and the reward system. Now, of course, our focus today is on substance use disorders, so we will return to discuss some key aspects of how the reward system is disrupted in severe substance use disorders. But first, let us turn our attention to the history of drug use and addictions.